As Hilary said, this is a work which I illustrated on Monday and which I then started carrying out. And for most of the week I was thinking I would cancel this talk anyway, because I was not getting anywhere. Yesterday I had my extended deadline to tell Hilary, sorry, I can't do it at all because I don't have any results. But then some results came in which were sort of telling a little bit of a story, at least some pretty pictures. And then I thought, well, maybe I don't cancel it just yet. And then it was too late to cancel it. And then I thought, okay, well, now I put something together. It's only half an hour anyway, and I hope it will be entertaining at least. And we'll hopefully be telling a little bit of a story. And you'll see what I was up to over this week, which was a little bit less interactive than I would have hoped to, because I was mostly working on my code, trying to get it to work and to get the numbers out. But I suppose that's just how it is, how it sometimes turns out. So this was my sort of motivation. Once I had the idea, I started reading around, and of course I had to find out it was already done and was already known about, at least in some sort of flavor, not necessarily in the flavor which I was thinking of. So the prognostic equations can be solved by integrating along the trajectories, which is different to the normal Semi-Lagrangian approach, where you've got a departure point and an arrival point, and you sort of hope that everything is fine in the middle. And then at several intermediate departure points, you would need to find the forcing by interpolation. By interpolating the forcing in space and in time. So this is sort of from a, I think, more internal report from John and Colin. And you have to ask them if they want to publish that still or not. But it's certainly available. So the motivation, I want to construct a local scheme which doesn't have global solves, because as we are all expecting, the future will not allow us to do global solves on the machines which are on the horizon. And then utilizing the anticipated infrastructure, I'm still saying anticipated, because I mean now we are thinking that they will be big, a lot of cores, and in 10 years time it will be all different again. It will be all one super high powerful processor, and then it will be all going to big super parallel machines again. And so the idea is that you take a local bit of memory, and then you do a lot of computation on this local bit of memory, and you can possibly even ship that local bit of memory out to a GPU, do a lot of trajectory integrations on a GPU, and then once you found the right answer, you get it back and you carry on. So that's sort of an idea I have in the back of my head, how this can be useful in the end. And then, of course, thinking about high resolution, local refinement. What are we going to see? Where are we going to find problems? Either you need to have very short trajectories, which capture the complexity of your flow, or you need complex trajectories, which follow the flow and therefore capture the complexity. And then you have other areas in your flow, which are large-scale, broad-scale flow, where your trajectory doesn't need to be so complex, but potentially very long. I mean, sort of to illustrate the idea, I was trying to do graphs yesterday, and I thought if I get into the computer, it takes me an hour to do the graph. If I try to sketch it here, it only takes me a couple of seconds. You've got a feature, you've got a surface here. So traditional weather feature, the atmosphere goes up in height. Then you've got a high updraft here, perhaps, some entrainment, I have to get my complexity, and some detrainment here. And now you've got a straight line trajectory, so you're rather limited of how you're going to resolve this. So you may, if you got a 4 meter per second wind, you're easily down in the ground with the endpoint of your trajectory. So you would really want to have trajectories which will be able to capture the flow as it actually happens, rather than just straight lines. And then, of course, here you've got the jet streams and you've got long trajectories. A straight line trajectory is perfectly fine there. And everything, even integrating along the trajectory or not, will converge very quickly there. And here you need the flexibility. So this would have taken me half an hour yesterday to do it on the computer. So what does it look like in equations? The integration, here just a prognostic h. In terms of shallow water, possibly not the best choice, but at the arrival point and at time delta t, so my time starts at 0 and I integrate until delta t, will then be computed by evaluating the departure point quantity and integrating from 0 to delta t. And this S is a source term, or our forcing functions, which are evaluated along the trajectory and interpolate it in time. So this is a time interpolation. And simultaneously, we solve the trajectory equation, where we evaluate the velocity field and time interpolate it, but evaluate it at the trajectory points. And this way we've got a nice coupled solution, and hopefully a very accurate solution. And the predictors are indicated here by the tilde, and they are just the normal forcing functions evaluated at the predictor. You can see them here on the right side of this fraction, where of course we don't know the values because this is our answer in the end once we've converged. So we need to have some predictors or an iterative procedure which then comes closer and closer to the right answer. So here I say it can either be a predictor or it can be the previous result of the iteration. Or if you don't use any fancy predictors, then it can as well be the result from the previous time step. So I use the shallow water equations as a model equation. And some time ago I tried to analyze this analytically and I didn't get very far. I think last night I realized what my mistake was. But so most of this work will be based, or all of this work will be based on numerical experimentations. So no analytical work yet, but I hope that I get there soon once I know. Yeah, I mean certainly that's the order where I'm coming from. So it feels more natural to me. So I've solved this on a one-dimensional periodic domain with some initial boundary with some initial conditions. So all the plots will be more or less showing the same thing. So I only need to explain it once. We've got the space dimension here and the time dimension here. Here you see the velocity field, and here you see the height field. And so this is now the singing and dancing result with all features which I've developed over this week enabled. But not all features. It doesn't use a fancy predictor, so it just uses the last time step result initially and then uses the result of the iteration for the time level n+1 estimate. And then it integrates along the trajectory and it does time interpolation. But you could as well imagine integrating along the trajectory without doing time interpolation. So then you would just have a purely explicit scheme and you would just capture the spatial variation but not any temporal changes. And this works very well. I'm quite happy with these results. And there's something missing here. Why is there an error plot here? This was meant to be here. Using the now auto-regressive predictor, for example, Berg algorithm is a fifth order polynomial in this case, to do the first guess for time level n+1, which works similarly well. I was hoping that it would work much better, especially in terms of the convergence of the iterative scheme. But you can see that there is not much difference here. So the plots to compare is this plot, where we just use the previous time level as initial guess for the first iteration. You can see that we converge rapidly with iterations. So time step 1, 2, 3, 4, 5, and then the iteration going down here. It's just fixed, set to the 10 iterations, and it seems to converge. I guess this is our machine precision limit we approach down here. And now with auto-regressive predictors, by eye you can hardly see the difference. There's like some reassuring difference that I don't have the same plot here. So there are some differences in the detail. And the thing to note here is that this is a fifth order polynomial, so we need 10 time steps in order to fully populate the time series. And you would expect the biggest difference at the end here, where we've got the time series fully populated. And you can see a little bit of an improvement, but not at all of the order of magnitude as I hoped. So focusing on this, we've got here about an order of magnitude perhaps difference between this point and this point. If you go back to this plot, they are all more or less at the same error level. So there's an improvement, but no magic there, unfortunately. Then I used fully explicit integration along the trajectory. That's what I said before, that we don't use any time interpolation. We just use a previous time steps result and integrate in integrate in space only. And you can see that very quickly we get into trouble here. So the integration did not continue past this point. And this is just the first sort of oscillation of the system. So not very far at all comparing to the, I don't know how many I've got here, but plenty of oscillations. So this is all done very close to the theoretical stability limit. And so we expect things to fail. But I didn't expect the explicit integration to fail this quickly, and the integration in space and time to perform that much better.
Does it fail to be a smaller time step?
With a smaller time step, I can integrate for longer, yes.
But it still blows up?
Eventually it's stable.
Okay.
I've got but it's a very small time step. I've got here reduce the time step by a factor of 10. It integrates much longer. I mean, there is trouble at the end here. You can't see it on the screen particularly well, but there's already a sort of checkerboard pattern coming in. But reducing it even further makes it stabler and integrate longer. Yeah.
You're starting with a very difficult problem with self-advection. So you're trying to predict the wind, and you're doing explicit, so you run into trouble. But one of your points was, okay, given the wind, how to do the advection if the wind evolution is given by something else that is stable.
Yeah.
So in your case, in the case you're presenting here, it's much more ambitious.
But closer to what we want to solve, more closer to the real problem which we want to solve.
You see, suppose that the wind is given by another model that is stable with a long time step, and you want to be advecting tracers, tons of tracers with following the wind. That's a different problem.
I want to propose this as well for momentum advection, not only for tracer advection. And then I have the problem that I have to advect the winds.
Then I think if you're proposing to use it as a proper trace momentum advection, you should complete the stability analysis that goes with it. It might be eventually stable with a small enough time step, but if you want to factor out what will be eventually the real cost of having this algorithm as the advection for the momentum, you need to know what are the constraints on the stability of the time step.
And so far, I see that the gravity wave limit is the stability limit of the method I've proposed, similar to.
So that's very bad because
well, it's not
vertical they are very fast.
Yes, but it's not worse than any other explicit method. It's not worse than any other explicit method. But we are sort of coming to the conclusion already before I have presented all the material.
There was the hope that the Semi-Lagrangian aspect would let you see the gravity wave step out, right?
Yeah, I was hoping that the increased accuracy.
The source term in the trajectory.
Yes, exactly. But not having the implicit solve still limits the time step.
To integrate state, I think you have to use implicitly the wind that you are going to use for trajectory computation. So if it's not implicit, you won't be able to use a long trajectory, long time step.
Yes, because I'm limited by the gravity wave speed.
Yeah.
If you're only following one characteristic, you have one characteristic in the problem, so that other one's always going to be for explicit scheme. It's just following the velocity characteristic.
Yep. And it is still an explicit scheme because there's no implicit solve in there. So I find that, well, my conclusion is, I gotta do the conclusion now and then I continue with the rest of my slides. The conclusion is that the stability is improved over a purely explicit scheme, but it's still by far not as good as a semi-implicit Semi-Lagrangian, because there is no implicit part in there. And I suppose it's not really that big of a surprise, but there was a hope that I would get significantly further than a normal explicit scheme, closer to the implicit Semi-Lagrangian semi-implicit performance. I get further than a fully explicit scheme, but not significantly further. So there's an improvement, but not an improvement as big as I hoped. So I will stop the conclusion here now and carry on with my slides, and then finish the rest part of my conclusion once I come to the conclusion. So purely explicit with a smaller time step, as expected, it works fine initially, but the errors will catch up with us and make the solution blow up. Reducing the time step even further gives us eventually amplification factor of smaller than 1, and then of course, as we expect, this solution is stable. Then I did some tests with constant advection because I was really wanting to push the trajectory without having too much gravity wave problems, and this enabled me to test the integration part along the trajectory, but it didn't really create a very long trajectory because, of course, I have a similar problem. The gravity waves are going to ruin my solution. I used constant velocity for the advection part in order to lengthen the trajectory. So a CFL of 0.4, I get a very good result. For some reason, yesterday the Runge-Kutta integrator wanted to stop there. I couldn't see anything wrong with the solution or the code. So this is still cause for further investigation why it exactly stopped there, but as far as I can see, everything looks fine. It produced a very nice answer. And with the
order of accuracy of RK integrator.
That's 2-3 at the moment. But I could go to higher, and I tried to go to a higher order, and it didn't integrate further either. So I have to look into detail what's going on there. I guess it's a technical problem. And with a CFL of 0.7, now you see it's really stretched out, and eventually it will not carry on integrating any further. I've got a detail view here, where you can at least see that there are still some nice waves forming there. So there's no sign of instability there, but they are going to mix with each other. And if I look at the maximum of the absolute values over the time steps, then I certainly see I've got an amplification factor of greater than 1. And which I, at the moment, guess is accumulation of grid scale energy, which is then eventually going to ruin my solution. And we see that our time step has to be limited by the expected relation dt over u naught square root gh. Again, I get much closer to this limit with the proposed scheme, but I cannot exceed it. And doing the same tests with a fully explicit scheme means that we have to stay even further away from this limit than we need to do with the proposed scheme. So summary, on Monday I had a long slide, now I thought I'd rather have 2 shorter slides. It's limited by gravity waves as expected, because it's an explicit scheme in the end, despite all iterations and despite the attempt to use predictors cleverly. It should still lend itself to a task-based parallel implementation, which is expected to work well on modern infrastructures. It captures a spatial variation, and I have some expectation that in high-resolution models and in locally refined models that is important. And as well, it will converge quickly in large-scale flow, which I think will be on benefit as well, because we don't need to invest much effort in areas where there's no complexity, whereas with traditional approaches you would solve the whole flow over the whole globe everywhere. at every iteration, and so this would free up computational cycles to use them where they are needed. And therefore can focus on strong transients. Then I've changed this to most parts of the atmosphere, more slowly varying. If I look out of the window now, and if I look out of the window 5 minutes later, I expect to see broadly the same features, and 5 minutes is still a very long time step for explicit methods, especially for high resolution explicit methods. So I still got hope that this is applicable. Now, of course, with cloud resolving, that may be different. And then what I haven't used this week, and what was still part of my idea, was to have an ensemble of predictions for the prognostics, and then integrate a trajectory for each ensemble member, and then evaluate the error and pick the best prediction. Which again was what I mentioned at the beginning, that you can take a local bit of memory, which is just big enough to hold your trajectory, how long it may be. I mean, you've got some estimate of how long it will be, and you can then estimate that chunk of memory which you need, ship that out to a GPU, fire 1,000, 10,000 trajectories, and then decide which one you want, and you only get one scalar back from the GPU to main memory, which I think would be an interesting application and something which would utilize future systems hopefully efficiently. And this is the end of my talk. Of course, saying that some form of implicitness is definitely needed, and maybe at some other point I will have time to work on my ideas on how to have a local implicit solve, and then supplement this method with a better predictor, which then hopefully gets over the gravity wave limit. Thank you very much for your attention, and I hope you found it interesting.
Any more comments or questions?
One thing to consider, that the GPUs are free computation, but I think it's not quite. You have to worry a lot about going into double precision and the number of operations. So there might be just an order of magnitude between the current algorithm and the speed that you would want to reach. But if you're losing that by using too much computation in the GPUs before transferring, you're not gaining much, and you might lose in the end.
But I don't really need to gain that much. The only thing I have to lose is a global implicit solve. If I lose that, I don't need to gain anything, because then I can utilize the next generation machine. I don't need to improve the local computation, because I just need to get rid of the bottleneck, which is a global communication, which is a global solve. And as soon as I can do that, I'm embarrassingly parallel. I only have nearest neighbor exchanges, and I can utilize the machine. I don't really need an order of magnitude improvement from going to the GPU. I just need the GPU to enable me to break the bottleneck.
What is the CFL limit for this idea? What is this value?
I ran into the CFL limit of 1.
1.
Yep.
So
It is the dx over v naught.
Yeah.
And I guess it's coming from the gravity waves, it's not coming from the advection. Because from the advection point of view, it should be fine. It's Semi-Lagrangian, so it doesn't matter how long your trajectory is.
What CFL do you want to get to?
Whatever is required. I mean, difficult to say, but you've got a high resolution area here. You can imagine you want to discretize this in very high resolution, and your CFL number will get higher and higher and higher, because the wind speed is sort of given, and you increase the resolution, and then the more resolution you have, the higher your CFL number.
But I mean, there's a physical limit to how much locality you can expect out of the system, because information propagates physically. And if you just can't get away from that barrier, it's got to come from a certain distance away. I mean, there is, I believe, some wisdom in trying to get away from the implicit solve, because that is truly global. So, for example, subcycling and explicit methods with explicit are limited only by the physical travel distance. So I think that's the wisest thing to be thinking about. But you can't break that physical. You have to have at least that much information. So you'll never be able to get away from that. So trying to go beyond some reasonable CFL numbers, unreasonable, I think, to expect that you could ever do that.
Without the global solve.
Without the global solve, and you have to ask yourself, if you're doing the global solve and it's becoming stable as CFLs, are you really solving the physical problem accurately? Right. So that's another story. So, I mean, the subcycling idea has worked for the shallow water gravity problem. People got a better performance out of it. I think it's Frankie did better subcycling with explicit solvers than did with the solvers for the implicit problem. That was just the lesson they learned.
One more quick comment from Jean.
And maybe the advection part, the trajectory part of the Semi-Lagrangian algorithm, I don't think is a global. It's a global computation. It's more local. What is global is stabilizing the long-range vertical waves.
Yeah, the advection part.
So the advection part is not global.
No, the advection part is just saying that the departure point quantity will be transported to the arrival point.
No, but you say, well, I don't want to do things globally. But, I want to avoid the cost of the global thing. But advection is not global.
Yes, but I'm not talking only about advection. If I would only be talking about advection, I wouldn't need to integrate along the trajectory. So I would just need to have an accurate trajectory and evaluate the departure point quantity. And then I would need to integrate along the trajectory for advection. Because I don't have any source terms along the trajectory. Oh yeah. I don't need to tell you, I'm sure, but just to make sure we're talking about the same thing. This is advection for me. And since the source term on the right-hand side is 0, I do not need to integrate along the trajectory, because I would integrate a lot of zeros.
You need to know the behavior of the wind and how the trajectory that will be followed. I mean, even if there's a 0 there, there's a UV, 0 dx written there, and a V, and so on. So you have to know the time story of the whole wind field to be able to integrate
For the
that.
trajectory, yes. But not for not for pure advection. But I think we're talking.
Okay, once you know the trajectory, you can use infinite time step.
Yeah.
I think we should move on, because I'm very embarrassed, but we have another talk at 10 o'clock, was it? Yes.
We have the speaker.
Oh, I'm sorry.
Have you laptop? Or do you want to use my laptop?
Can you come set up?
Yeah.